Questions? Oh, yeah. No, I won't look at the hand. Yes.
Section 2.1, number 7.
2.17. Which part? Any of them?
Well, I understand A and B, but the rest of them, I don't understand. It seems kind of random. The answers in the back of the book seem kind of random.
Okay, so if I gave you, say, set S1 was made up of the letter A, square. Is a square an element of S1? That's true. Now, what if I did S1 is made up of, say, 1A, the set of the square. Is square an element of yes or no? All right, I'm going to make a, what are the elements? The elements are the things separated by commas, right? And so the primary commas, because the comma itself could be part of an element, right? And so that is an element, that is an element, and that is an element. That is an element, that is an element, that is an element. Element of is the question, is it literally exactly and only that there? Is square in S2? No. Right? Because what is there? This symbol is there, this symbol is there, and yes, it's complicated, but that symbol, which is made of 3 components, which actually represents what? A set, right? Does that make sense? Yeah. So what can go on inside of these things? So for this problem, we look at it, the question is, for each of these, for number 7, the question is 2, and what you see, an element of the set? No, so let's get one that's like, for example, like D. 7D, the set that we're looking at is the set where the first element is a set with the number 2 in it, and the next element is a set of a set. Right, so that's one element and that's one element. My first element is a set that has a number 2 in it, and the next element is a set that has a set with a number 2 in it. Kind of oddball looking, but those are one thing. One uses 3 symbols, one uses 5 symbols. Right? But those are one object of 5 symbols. And you could look at this and say, look, the cardinality of S is 2. There's only 2 objects in it. It's a multi-symbol, right? And so the answer would be 2 is not in S. Now, that's what you have to look for, is 2 all by itself or not. And sometimes if you would use words and things like, for example, is A in S, is that a question? So for example, if I said S was made up of, say, Mark and B and at, yes or no? No, because I'm looking for A all by itself, but I see an A. No. A all by itself. And so the answer here is like A is not in S. B is in S, right? At is in S. Is everyone okay with that? And so, yeah, they're getting tricky because you do things like power sets of power sets, and so you see things like number 10, where like, is the empty set here, or is the empty set of the empty set, which is the set. And they have fun doing things like that, and you can do power sets. You could say things like, I wonder what is the power set of the empty set? Things like that. What does that equal to? So you get sets of sets, and what would be its cardinality, and kind of go through it. But anyways, They play, I mean, it's one of those things where you can just kind of goof around a little bit. Any other questions? Does that answer your question?
Yeah.
Okay.
Thank you.
Yes, sir.
This is question number 25 from 2.1.
2125. Okay. If you want to show an if and only if, so 2.1, number 25, if you want to prove that the power set of a set A is a subset of the power set of the set B, if and only if A is a subset of B. Right, if and only if is a biconditional. So if I ask you to prove a biconditional, there's two approaches. The left is logically equivalent to step 1, which is logically equivalent to step 2, which is logically equivalent to bunches of steps until you get to the right. That typically doesn't happen. That's probably not going. It's not going to happen here. And so if I want to prove this, we're going to do two cases. We would do case 1. Let's take the right implies the left, which is A is a subset of B implies that the power set of A is a subset of the power set of B. And then we would have case 2, that the power set of A is a subset of the power set of B, and show that that means that A must be a subset of B. So we'd actually want to do both of those cases. What's subset mean? I mean, I see this, but I can't prove something unless I know what I'm talking about, right? How do you show implications directly? You know, I could prove both of these directly. We could try contraposition. We could try contrapositive. But there's certain things that if I look at this and if I don't know what my symbols mean, there's no point in trying, right? So a little bit of note. What does it mean for set 1 to be a subset of set 2? What does that mean logically? For all elements, if the element is in set 1, then the element is in set 2. Is everybody okay with that? That's what the word subset means. Now, many times on this, and we could actually do that, if this is understood, it's like, I know what you mean. Stop saying all elements. If everybody agrees that we understand all elements, a lot of times you would just simply write that, right? If we all agree that we're universal statement, I don't want to keep writing it, that's lazy mathematician behavior, that's fine, right? That's one thing that we have to note. The other thing is, what is this? It's the power set, which is the set of all subsets of S, right? How do you normally generate the power set? What's the very first row? The empty set. The next row? The singletons, right? The next row? The duals. The next one? All triples until what's the bottom row? The entire set S, right? That's normally how we write the power set, right? So kind of keep that in the back of our mind. We have the empty set, the singletons, the duals, until we'll finally get down to the subset. Okay, what are we asked to show? Right? What's that mean? If I assumed it, what would it mean? Because I'm going to assume the left and show the right. Everything in A is in B. All the elements of A are an element of B. And that's supposed to show what? Everything that's in the power, or what is that? What's the power set? All subsets of A. So what does it mean to be in A's power set? That means everything in the left is in the right. What's in the left? All the subsets of A. What's the thing on the right? All the subsets of B. So what am I trying to show finally? Case 1 says this. If all of the elements in A are an element of B, does that naturally imply that every possible subset of A is actually a subset of B? All right, now let's think a second for, does that seem to make sense? All right, what does it mean to be an element of A? Well, I have a bucket of A, right? I have all these little A's in it, and then it's inside of a bigger bucket, which is B, right? I have these nesting of buckets. That's what the left-hand side says. What's the right-hand side say? What's a subset of A? If all of bucket A is inside of bucket B, what's a subset? Let's take a few of those, or all of them, or none of them. Some of those, doesn't matter which I take, it's going to be a subset of A. Is that still inside of B's bucket? Yeah, that seems to make sense, but we're going to have to prove that. All right, what's the second case? If somebody came up to you and said, all right, I noticed that you have all of A's subsets. And I noticed that every one of those subsets is actually a subset of B. The only way that can happen is if all of A's elements are actually B's elements that's inside of it. And that's what we're asked to show. All right, so how are we going to do it? So all of that work, that talking, that visualization, thinking of sets and buckets, and maybe even writing little scraps of paper down and like making sets and buckets, and even that might seem childish, we have to think in our head, what do the symbols mean and what do they represent? If we cannot visualize it, there's no point in trying to prove. Now that's me. Other people are very much symbol people. And there are some people that just love college algebra because they like to mess with symbols. Look at these X's and they become those X's in factoring. It's really cool to follow the rules and shapes become new shapes. That's not all of us, but if you're okay with that, all right. Let's try case 1. I want to show that A is a subset of B implies that the power set of A is a subset of the power set of B. I'm going to try a direct proof. So a direct proof is I'm just going to go ahead and assume that A is a subset of B. Right? Assume the left share the right. What does that mean? That actually means that if an element is in A, then the element is in B. Everybody okay with that? In the back of my mind, what's the goal? That power set of A is a subset of the power set of B. But again, what does that actually mean? That if something is in the left, what's an element of the left? Subset, right? So that's saying that if a set is in the power set of A, that implies that set is in the power set of B. This is kind of this is this is backward reasoning. I'm starting with what I want, and I'm asking, what does that mean? Okay, well, what does it mean to be in the power set? It's a subset, right? So that actually means, but that actually means that S is simply a subset of A. And that should imply S is a set of B. So what's your real goal? Your real goal is to say that if you have a subset of A, then it's actually a subset of B. That's what that means. Now, did that jump out right away, that this symbology really meant that? Okay, is everybody okay with that's what it means? I verbalized it, now I wrote it. Is that true? Okay. This is given, right? This is what we assumed. That's the inductive hypothesis. And what do I want to show? The bottom. Okay, how do I show implications? This is where I want to get. Start at the left and get to the right. Okay. All right, so this is the backwards part, so let's go ahead and start it. If S is a subset of A, right, means that all E that are in S are in A, right? So I have a subset, I have an element of the power set. Okay. But by the inductive hypothesis, right, by the assumption, sorry, not the inductive hypothesis. By direct assumption, what do I assume? If you're in A, where are you? In B. But all the A's are B's. So that tells me that, yes, everything is in S means that it's in A. But that simply also says that E must be in B. Which tells me what? It's a subset of B. So we're done. Zero K. This is exactly what I said originally as the bucket. If you look in the back, they write it a little bit differently in terms of their notation. But what does it mean? You have a subset of A. Subsets of A are made up of elements of A. Well, everything in A is in B, so that means you're an element of B, so it has to be a subset of B, so we're good. Everybody okay with that? Okay, what about the other direction? The other direction, in terms of case 2, the idea behind case 2 here, I would like this. This is true. I'm going to assume that, and I want to show that. And the way that we do that is to say we're going to pick some special subsets. This says all the subsets of A must be subsets of B. But on the right-hand side, it only wants to talk about single elements, right? All by themselves. So what is the second row of the power set? If the first row is a set of no elements, the second row is all of the what? The singletons. So this part right here says, well, this is always true. Well, fine. Let's take the singletons of A. Right? All the singletons of A have to be singletons of who? B. But the singletons are the who? A's elements. Well, that means that they must be B's elements. So by only focusing on the singletons, that second part, A is a subset of B, comes from the singleton. Just don't focus on all of them, just focus on the singletons. And that's enough. And so it works. But that's the idea behind that case, is they focus on the singleton.
So why do you choose those?
Because what's our desire? What's our goal? Our goal is elements of A need to be elements of B, right? Which is elements all by themselves, right? And so by taking the singletons, right, that would be this singleton set all by itself is like element 1 is in A. Well, that would mean element 1 must be a subset of B. But what does it mean to be a subset? Well, if it's a singleton, that means it's one of the elements. Oh, an element in A is an element in B. So it immediately comes out. The idea behind that would be this. A set all by itself, right, that's a singleton, is obviously a subset of A, right? And then because the power set of A is a subset of the power set of B, because that is true, that implies that that element must also be a subset of B. But now that you look at that, if E all by itself is a subset of A, what does that tell you about E? It's in A. If E all by itself is a subset of B, what does that tell you about E? It's in B. Because they're singletons, an element in A implies elements in B, which is what we wanted. And since I never did say which element, I proved them all. Right? What's E? Any element of A. That's the idea behind it. You just have to write it down a little bit cleaner. That's one of the nicer proofs. I like that one because it's a biconditional, and it makes you think long and hard what the symbols mean. Like P of S, what does that even mean? All right, what does it mean? All right, 2.3. 2.3 is kind of a jump ahead, so I'll just go ahead and jump ahead to the second semester for a few minutes, and then we'll pull it back. We're inside of set theory, and what we're going to do is we're going to pull out a piece of sets and look at special types of sets. For sets themselves, we looked at one particular operation, which was the cross product, A1 cross A2 cross everything up to AN, which is the set of all n tuples A1, A2 up to AN, such that the A sub I is taken from A sub I. And so this is the set of all possible n tuples. Given that we have all possible n tuples here, one of the things that you could look at the set of all n tuples is we could ask a particular question about, what about subsets? Subsets of all possible n tuples. So we could look at an example of, let's say we did a 3-tuple where A1 was made up of the numbers 1 to up to 10. Say A2 is A, B, up to Z, and say A3 is made up of all of the polyhedrons, so triangles and squares and pentagons up to a dodecagon, right? 12-sided object, and so we had that. And so what would be the cross product? The cross product would all be 10 times 26 times 12 total ordered triples, where you would pick a number, pick a letter, pick a shape. And it would be all 10 times 26 times 12 ways to pick a number and a letter and a shape. Well, a subset would be something like this. Maybe somebody simply says, okay, let's pick it in the following way. Let's pick a number. I'm going to pick a number, I'm going to pick a letter, and then I'm going to pick a shape, and then I'm going to pick the number, and then, oh, I got a better letter. I'm going to pick the letter T, because it starts as a triangle, 4 square and a square, right? And so I make, all the different ways of having a number, 5, pentagon, and then make the pentagon, right? Everybody catch my rule? This is a subset, right? In my rule is what I'm doing is I'm picking the number of sides, the letter of what the word is, triangle, square, pentagon, sextagon, septagon, octagon, nonagon, dodecagon, right? Which would be 12D dodecagon shape, right? And that's just obviously a subset. But if I look at this particular rule, there's a reason why I picked these triples. these triples form, if I would look at it, these form, this set is a relationship. Between the sets. I had a reason for it, but it makes a relationship. And normally, if you would say three shapes, you would say for this between, you would actually say this is what's called a three-ary relation. Whatever the reason is, I would call it a three-ary relation. All right, we can have fun with that. I could sit there and say that, you know what, there is a student, clothing, chair, book, phone relationship that happened to make this class occur. Or how about let's make it simple, student, chair. All right? Some relationship happened to make you sit where you sat. Now, like this one, everybody sees the relationship. I picked a number, a letter, and a shape, and everybody can catch it. Could you imagine trying to figure out what happened to make you sit where you sat today? All right? And try to write it down. Give me the rule that made this happen. All right, maybe make your brain hurt, right? A little bit on things like that. But in the end, it's still just a relationship. And so when we study such things and we go to what's called any of these subsets, they would be called an Nri relation. Nri relations are just simply sets of n tuples. Basically, they're subsets of the cross product. We're just going to take some of them. The cross product represents every possible way you could ever do anything. What would be a relationship? Well, let's start taking some of those, which would be the cardinality of the power set. So this is pretty big. The study of such things is relational databases. All a relational database is this set. And if we look at this and say, boy, that's hard. If I tried to get students, clothing, phones, chairs, shoes, glasses, right, to make this class happen, all right, I don't even want to think about something that big. And so normally what we would start to do is try and say, okay, let's make our problem easier. So the first thing we do to make the problem easier is to go from Nri relations, and to try to make an easier question is we go to two-ary, or what's called a binary relation. Without doubt, we just usually say, or just simply say, relation. So if a person normally says relation, they mean binary relation. If there's a doubt, it's like, well, did you mean three-ary? No, I meant binary, so I'll say binary, which means two. What's nice about binary relations is this gives us a nice feature. We have our two sets. I have set A, I have set B. I have my relationship that goes from A to B. Well, AB is a thing that's in my relationship, and so I can visualize it in this way. That I go from A to B, and I can say that, why? Because there's only two sets, right? And they're ordered pairs. There's a first and a second, and we normally write it like this. Relationships go from one set to another set. So it's nice. We can actually write it in nice, clean relationships. What's A normally called? Set A. What do we normally call the first set of a relationship? The function is the rule, well, not a function, but the relationship is the rule that maps, right? There's a relationship of some sort. But we normally say that where you're coming from is the domain, and where you're going to is the codomain. It's the co with the domain. All right, that's still too hard. We don't like it because, well, I could draw, since these relationships are functions, right? Well, I'm jumping too far ahead. These relationships are sets, and sets are collections of ordered pairs, right? So how could I write these collections of ordered pairs? We could use roster, list all the ordered pairs. we could give me a rule of some sort, which is set builder notation, right? Some way of defining when it's in or when it's not. But this actually adds an additional way, which is graphing. We could actually do the sets to represent it. The first way we could do is just simply list it out. R is made up of, say, A goes to B, A goes to C, etc. You know, whatever you want to do for your ordered pairs, just list them all out. Q goes to R, right? 2, we could do set builder. Set builder would be, say, all relations are made up of ordered pairs, say, x, y, such that y is equal to x squared minus 1, right? And say, and I'm not saying that the following, but x, y are real numbers, right? So I have some real numbers, and y is always equal to x squared minus 1. A lot of times in calculus, right, all we wrote was the rule. We didn't give the fact that, no, a function, what we call functions in calculus, is a relationship, is actually the ordered pairs. It's not the rule, but the rule is the thing that generates the ordered pairs. So set builder notation, what's the big part? The rules. So we normally just write the rules, start messing around with the rules. Okay, so we usually do set builder notation. So a lot of times we'll just write the rule. And the third would be graphs. And there's kind of a couple ways of doing graphs. I could do this. I could notice that, okay, -1 goes to 0, 0 goes to -1, 1 goes up to 0 again, 2 would go over here to, let me see, what would that be, 3, right, etc. Right? We could do, if, here's kind of an interesting question. If you see the pattern, ellipsis is allowed. If you do not see the pattern, ellipsis is not allowed. Right? So I could use an arrow graph, but that's a graph. Other ways that we're more used to writing it would be this, right? That's still an arrow graph. Look at this. This is the number 2. Goes up here, goes over there. There's a 3. And this is the point 2, 3. What did it mean? Well, if y was equal to x squared minus 1, graphs are collections of ordered pairs. What are the ordered pairs? They're actually an arrow diagram. 2 has gone to 3. So what we call graphs and what we've done before is just really what? A different way of writing our sets of ordered pairs. We visualize it. All right, so those are all still relations. These are a little bit too complicated. We're going to simplify it down. Let's go one more level of easier. The one more level of easier is to get to functions. Functions are between two sets where we have a domain and a codomain. But we have the following restriction. It's a relationship. So it's a relation that assigns exactly one B of B to each A of A. Two restrictions to make our life simpler. If when you map your A to B, you get to go exactly 1. Okay, what does this mean? We have two problems that happen. One, if your little a tries to go to more than one place, right, like this and this and this, this is not a function. Is it a relationship? Sure. Can one student sit in 10 chairs? Yeah, just spread all out. Those are my chairs. Don't sit there. It's mine. Not a function. Function says one student sits in one chair. Well, I want to put my feet up. One chair. Get your feet down. Well, I want to put my book bag over there. One chair. Right? The other thing would be this. If we have this and we go all the way across and they start mapping, well, maybe we have two students sit in one chair, This student sits in his favorite chair, okay? And then we have this other student goes over and shares a chair with him, but I notice that student don't go anywhere. That's true. Wait, you're standing up? Yes, I don't want to sit. Not a function. Those are my two restrictions. Everybody sit down. And you get one chair. That's a function. My other favorite one is every student gets a gun. We line up all the teachers. Right? What's the rule? Everybody has to shoot. Right? And number 2, no trick shots. No, I can hit 2 teachers at the same time. No, you can't. 1 teacher. Right? That's fine. All right, this also introduces, when I said the domain, came another question. A lot of people said, domain range. And I said it was domain codomain. Okay, what's the range? All right, the range is part of the codomain. It's a subset of the codomain. Range is a subset of the codomain. But if we go back to shooting teachers, what's the codomain? The teacher's in the front of the room. What is the range? Who did you shoot? Everybody else who wasn't shoot, they're part of the codomain, but they're not part of the range. It's the people, for example, if it's the chairs. Right? What's the codomain? All the chairs. What's the range? The ones you're sitting in. Well, that's an empty one. That's an empty one. That's part of the codomain. It's not part of the range. If we would visualize it, a lot of times you would look at it this way. Let's say that on the left-hand side, at this point, I have a straight line over here, and this one kind of goes up and does that, right? We'll say this is down here at -2. All right, what's the domain? What are all the numbers from left to right? It's supposed to be what? From -infinity to +infinity. I would assume that everybody can catch the ellipsis, right? That's the nice thing about graphs like this. We can usually see it. All right, what is the codomain? -infinity to infinity. What's the range? -2 to infinity. Is everybody okay with that? So the domain is all R. The codomain is all R. But the range is going from -2 including up to infinity. It also introduces something where, let's say we have a problem like this, and if we notice that, it ends up that if we would look at calculus, calculus is the study of at least Calc 1 and 2. It's the study of functions from reals to reals, right? We did all of this work, and we had functions that just simply mapped reals to reals. Well, we didn't say we have to, let's graph it. What's the max and min, right? And we looked at this. It ends up being that this here, under calculus, is your new math toy. And then we had, guess what? Rules. And what did you learn in calculus? Well, what's your new toy? Functions. We were introducing algebra. We didn't. I doubt your calculus instructor, unless you had me for Calc 1, Calc 2, is to say, okay, what is this? Math is about toys and rules. What's your new toy? It's functions. What are functions? It's rules that map reals to reals. All right, and what are we going to do with them? Well, what did you learn from these things? We learned, well, maybe I could take one function and add another function. Maybe I can take one function and multiply another function. Maybe I can take one function and compose it with another function. Right? Oh, yep. No, there are enough people here now. So, for every one of these end up being that, well, if these are reals to reals, we could sit there and, oops. There we go. Move this over. We could actually take each of these, and they would become, okay, I want it to be a function. And it seems to naturally define that we would do this addition here. And then, oh, I bet this is easy enough. This would be just simply f1 of x times f2 of x And this one here, under composition, is f1 of f2 of x, right? And it was as we read it. And so these are all just straightforward reviews. What else did we learn in calculus to do to functions besides? This is algebra stuff. Here's an interesting feature. Same symbol. Are they the same thing? The plus on the left is a question of this rule plus this rule. Well, what does that mean? Well, we look to the right-hand side and say, I understand what in the codomain of reals plus means. It's a real number plus a real number. So it ends up being that, how do you have your two rules add? What I really mean is ask, follow the first rule, get a number, follow the second rule, get a number, add those two numbers, and that's where you go. So the plus is a different type of plus, but we defined it that way. And it's still a function. So we always have to worry a little bit as you do your notation. And the other things in calculus you learned is derivatives. What happens? A function comes in, a function comes out. Integration. A function comes in, a function comes out. We had reasons for it, finding slopes and areas and antiderivatives. But in the end, it's just toys and rules. You're just messing around with functions. You're playing with these rules. And they have some rather interesting applications. All right, what are some special functions that we should know? All right, the first is we could break them into classifications. The idea of 1 to 1. If you're in calculus and you did a graph that passes the vertical line test, it's a function. If it passes the horizontal line test, it is a 1-to-1, right? Or an injective function. What does it mean to be 1-to-1? That would mean that for all A, for all B, if the A and the B map to the same place, it only happened because they came from the same place. Which is logically the same as what? What is the contraposition of that statement? If A is not B, then where they map is different. Probably easier to think about. Two different starting places, two different ending places. That's the idea of 1-to-1. That means that if you go there, that's, for example, that's your chair. We have a 1-to-1 function because you're not sharing with anybody. It's your chair. No one else gets to get into it. So that's 1-to-1 functions. 2, onto. What does it mean to be an onto? That, well, for everything that's in the codomain that you look at, you could go back and find something in the domain such that it is mapped to that element in the codomain. Another way of looking at this is range equals codomain. In terms of words, left-hand side is a preimage, right-hand side is an image that says all the images have a preimage. So everything in the codomain has a preimage. All right, now if it was both, 1-to-1 and onto, this is called a bijection. 1-to-1 is injection, onto is surjection. 1-to-1 and onto is a bijection. All right, why would we want things, and we want to have these particular functions that are 1-to-1 onto, or possibly 1-to-1 and onto? Why are we interested in it? Well, if we go back to our composition, and if we would say that, okay, I have functions f, I don't know, for sake of r onto r, if we would look at it this way. And over here, we have the real numbers, and over here, we have the real numbers. And I notice that I go across, and here's a function f, and I'm going from A to B. One of the things that we would like to sometimes do, and we do this a lot in mathematics, is how do I undo a particular process? When we would take problems and say, in math, a common question is how to undo an operation. Now, why, we could ask in a bit, but let's say we had things like, okay, can anybody tell me what the solution is to that? I look at it and I say, I'm pretty sure the only number that works is 3. And then we're all happy, right? But what if I did this? And I asked, what's the solution to that? Now, we're all smart enough. We land, all right, but my problem is the left was nice because x was by itself, right? Now look at the right-hand side. I don't have x by itself. I've done something to it. I added 2 to my number. And then the question was, life would have been better if you didn't do that. Why'd you add 2? I don't know. It's like, well, okay, undo it. You did that, undo it. It's like, well, if I did that, undo it, what do I mean by that? Well, how do we undo a process? Well, undoing a process is, can I do the identity? What's an identity? An identity is a do nothing. Could I go from a +2 to a +0? And so when we go through here and we say things like, please subtract 2 from both sides, what did you really do? You said, under this operation, can you imply an inverse that forms an identity that does nothing? And we're going to do that all the time in math, right? Undo this. Well, how do I do that? What's the inverse operation to form the identity to get back to where you want it? And we do that in linear algebra. We do that in arithmetic. We do that in algebra. We do that in calculus. And how do we do it in calculus? We need to, well, what if I had a function? Say, what if I had e to the x is equal to 4? I say, solve for x. And you're like, well, I took the exponential. Don't do that. Well, how do you get rid of it? What is the inverse operator of the exponential function? Natural log. And so, okay, fine. I'll take the natural log of the left. I'll take the natural log of the right. That's just x is equal to the natural log of 4, and I get my answer. Why? Because I undid it. But here's my question. How did you know that the answer was the natural log? How did you know it was the inverse function? Well, if I'm looking for inverse functions, how do you calculate them? Well, what we're looking for is if f goes from here to here, I need to go backwards according to its inverse, right? This is not f to the -1 power. It's just a label, right? Because how do you inverse addition? You subtract. How do you inverse multiplication? You divide, but that's the -1 power. Well, -1 shows up a lot. Okay, I'm going to use that as my label. Instead of saying that f and the inverse function is, well, I don't know, they could have done this, put a little I up there, or it's the inverse of that function. They could put a little hat on it to say it's the inverse function. They don't. They write -1 to confuse you, to make, oh, no, it's not. It's a label. It's the undo function. What has to be true about f for the inverse to exist? Not all things have inverses, only ones that are 1-to-1 and onto. If they are not 1-to-1 and they are not onto, there is no inverse function. Not all things are invertible. What's the multiplicative inverse of 0? Doesn't have one. right? Not everything works. So as long as F is bijective, F inverse exists, and F composed with F inverse is the identity, which is just simply X, and F inverse composed with F is also the identity, because they're inverse functions of one another. We're not going to ask you to find it, it's just it exists. So, all right, for attendance, that'll be 2.3, number 21. And I want the manila envelope. You can keep the exam is yours. I want the manila envelope so I can use it again next time. You can go ahead and hand those up with your attendance. You can't tell, I reuse them.
Yeah,